So in addition to the long name, we've got a long list of authors and contributors that wouldn't fit on the first page. So here's the rest of the first page. So what we'll talk about for the next little while are the motivations behind what the proposal is that I'm going to be laying out for you. Talk a bit about ATSC 3 SFNs and LDM and their potential relationship. Using LDM then for wireless in-band distribution, one of the bigger issues that distribution being one of the bigger issues that we deal with in SFNs. Some implementation challenges for the proposal, some potential future extensions, and the inevitable conclusions. So the motivations for this originate with the idea that ATSC 3 is a very good system for delivering signals to mobile receivers. And that such receivers will become increasingly important for TV broadcasting. Delivering signals, robust signals to mobile devices, though, is always challenging and inevitably leads to the need for single frequency networks if you're going to have signal levels that are uniform enough throughout a service area to deliver reliable service to mobile or handheld devices. One possibility that presents itself is that you can have some very low cost, especially with ATSC 3, you can have some very low cost SFN gap fillers in places that you wouldn't have thought about putting transmitters previously. And I'll show you some examples on the next page. And you can do that with very inexpensive equipment, but somehow you've got to deliver the signals to those locations. And delivering backhaul to SFN transmitters can be both problematic and expensive, typically involving either microwave links, for which spectrum can be scarce or installation costs can be high, or fiber links. If you don't have a fiber near where you want it, then you get into expensive construction costs or high rents. And a third one would be satellites. I've done all three of these, and satellites, while at the beginning is the least expensive, operationally can be the most expensive. I'd just point out that when I first came up with the idea of SFNs for digital television in 1990, we spent the next couple of years in the committee I was chairing in the FCC Advisory Committee looking at the practicalities of SFN and whether or not it would be a workable technique. And technically, we could make it work. When we got into the cost structure, the distribution costs were the things that was the thing that had the greatest impact on whether or not it would be implementable going forward. Now, those costs have come way down, but they still can be, especially when we get into really low power transmitters and low cost transmitters, that can still be the determining factor on whether or not you can afford to do something. So the kinds of places, oh, I forgot about those. So just as I was saying, there's a potential cost and resource availability issue for SFN distribution. A good solution very well may be to use wireless distribution links in band. So sharing the same channel with the broadcast that we're sending to those mobile receivers. And so what I'm going to be going through is a proposal for wireless in-band backhaul using LDM as the mechanism for getting the signals through the channel. The kinds of places that we're talking about are, for instance, shopping centers or subway stations or cars, train stations, airports, stadia, coliseums, places like that that are isolated from normal high-power transmitters, and where you still have enough of a population density that you want to be able to reach the devices that people are carrying with them. So one way to do that is with LDM. And just for background, LDM is a way of transmitting multiple signals that are partially independent of one another at different power levels, in layers within a signal. So when it says here non-orthogonal multiplexing, that means that there is some dependency between the two layers that we're talking about, the core layer and the enhanced layer in particular. And you can use the symbols run at the same instance. And so that means that you can receive the high power layer, the core layer, and once you've locked to it, you can then use that lock to decode and recover the enhanced layer. So the two of them operate synchronously with one another. Their periods and key instance are the same, but you could have completely different modulation constellations. You could have completely different coding in the two layers in order to make, for instance, the core layer very robust for mobile applications and needing a very low signal-to-noise ratio in order to be receivable, while you use the enhanced layer with a much denser constellation, and you could, it would have a much higher required signal-to-noise ratio, but you can still recover it even though it's buried beneath the core layer, because you receive the core layer, reconstruct it, subtract it from the signal, and now you're left with the enhanced layer clean so that you can recover it. So that's the way LDM works. And especially since we've now got much greater advances in video coding, for instance, we can put a lot more into that space. And for instance, as it says here, 4 or 6 HD video sources, or you could put the 4K extensions in SHVC, and still have some room left over to carry other data, and that's what we're going to be using. So in this case, we'll use the enhanced layer for our wireless distribution link, and use and that'll be distribution from one transmitter to another transmitter in order to build an SFN. And at the same time, we'll have the core layer from all of those transmitters delivering essentially SFN signals for mobile reception. So here's a current structure for an SFN. We come into a broadcast gateway. The gateway has the ability to send LDM physical layer pipes to the ATSC3 exciter. In this instance, we've got a high power transmitter that we're calling TXA, and that is feeding consumer devices. Let's see, does this have a pointer? Oops. Sorry. I'm trying to find the button for the, oh, there's the pointer button. So here's TXA, high power, and we want to add a couple of smaller transmitters for the kinds of applications that I showed on the earlier page with all the photos. And so we've shown a couple of those here. Today, what we would have to do is run a normal STL, be it microwave or fiber or even satellite, to the high power TXA, and we'd also then have to run microwave or fiber into the shopping center or into the subway station or wherever we're going. And it's that distribution link that is really expensive, especially compared to what the cost of these exciters is going to become over time, and if we're able to use as many of them as it looks like we could actively engage in systems. So what we'd like to do, I guess I have to go this way, what we'd like to do is eliminate the cost of those. And in order to do that, what we're looking at is a network that looks more like this. And so what we do is we have the gateway, again, developing a PLP or multiple PLPs on the enhanced layer of the LDM signal, feeding the exciter for transmitter A, excuse me. But instead of having those microwave or fiber links to the small individual locations for the gap filler transmitters, the low power transmitters, we put that signal into the lower layer of the LDM, the enhanced layer, and use it to feed each of the sites. We've added a relay receiver at each of these sites, and I'll talk about that in detail in a minute. And so the core layer is transmitted from transmitter A and transmitter B and transmitter C, and forms a single frequency network to deliver signals to mobile devices. And we use the enhanced layer of transmitter A, the high power transmitter, both to deliver, for example, 4K enhancement for fixed service reception, and also to deliver the STL data to the gap filler transmitters at both of these locations. And so there's part of that enhanced layer that's intended for consumer reception, and part of it that's intended for reception at other transmission sites. So the relay receiver, there's one at each site where we're going to put gap fillers. It receives a high power signal. It uses something called the transmitter identifier, or transmitter ID, that's emitted by ATSC 3 signals to get the channel impulse response of both transmitters that it's going to be seeing. It's going to be seeing the signal coming from transmitter A that I was showing, and it's going to be seeing the signal coming from its own transmitter feeding back into its input antenna. And so we've got to be able to cancel that signal out, and we'll get into this a little more in another slide. But in order to separate those two signals out, so signals from one another, so that we can properly equalize the channel and recover the data from coming from transmitter A, while at the same time rejecting the self-interference from the transmitter that's co-located with the relay receiver, we need to get those two channel impulse responses, and we can do that very well using the transmitter ID that's buried many dB under those two signals. The next thing that the relay receiver does is to recover all of that enhanced layer data, both the STL data and the data for fixed reception, and then it selects the STL data, the STL-TP or transport protocol data, and then feeds that STL-TP data, which is identical to what goes to every other transmitter. It's just nested inside the signal that's fed to the first transmitter, TXA, or transmitters if we have multiple high-power transmitters in the SFN. It feeds that STL-TP data to the exciters, and the exciters are just like any other exciters, and they're getting the same input every other exciter gets. So in order to do this, this requires that the receiver be isolated from that SFN gap filler transmission, and in order to do that, we can do a couple things. We use high gain, high directivity receiving antennas, and we also then do the cancellation of the interference, the self-interference, using the TXID channel impulse response. And note that depending on the site, we might have one relay receiver and many gap filler transmitters that we could feed from it, to wherever we can run the wire between the two. So if we look at the data that's transmitted, the core layer on top, that's the high power layer, is carrying the mobile services. And the enhanced layer, which is the lower power one, is carrying some data for fixed services and also the mobile service STL side by side. And those could share a physical layer pipe, or those could be in separate physical layer pipes. Either way it'll work. So in this particular case, notice I've called this case 1, because I'll tell you about case 2 later on. In this case 1, we have the core layer emitted by all transmitters. And the enhancement layer is only emitted by the high power SFN transmitters. And the implication of that is that if you were trying to receive the fixed data and we were to transmit it from, and you were near to one of the gap fillers, the effective power level of the enhanced layer would be reduced. And so that'll be important when we get to case 2. So if we look at the amount of capacity that the STL data carries, you can see that we have a number of different ways we can configure this. So row 1 is assuming that we're delivering 2.7 megabits to a mobile service. Row 2 is assuming that we're delivering 4.1 megabits to a mobile service. And that would be transmitted by all of the transmitters in the network. Now we can choose how much capacity we use for delivery of the backhaul data, the STL-TP data, to those gap fillers by changing the modulation constellation and the coding that we use for the STL-TP data in the enhanced layer. And so we can, if we start with a much more robust kind of delivery, for instance using 16 QAM, we would chew up 50% of that channel. If we move to higher and higher orders of modulation, we can get it down to 10% if we're using 256 QAM at the 2.7 megabit level, or if we can again use 10% and deliver 4.1 megabits if we use 1K QAM, 1024 points in the constellation. We can get all the way, if we really want to work at it, we can get all the way down to 5% enhanced layer capacity utilized for delivering these two levels of data for mobile reception by using 1K QAM with a higher coding rate, and that'll get us to 5%. Or if we go all the way to 4K QAM and 4.1 megabits, we end up using either 8.3 or 7.7% of that enhanced layer, depending on which channel coding we're using. So if you want to receive 4K QAM, you have to have a pretty good connection between the two sites. It's got to be a really low noise delivery because it's not going to be very robust. It's going to take a pretty high signal-to-noise ratio to receive that dense a constellation. So we need some new functionality in particular in the gateways and also in the gap fillers. We need to carry that STL-TP data in a PLP that's included in the enhanced layer. Fundamentally, what that means is that the broadcast gateway has to generate a second copy of the STL-TP data and send it to the high-power SFN transmitters for retransmission to the gap fillers. and that'll be an enhanced layer. You can think of it as nested. In terms of the STLTP going to those transmitters, you can think of it as a nested STLTP inside another STLTP. And that gets it then to where it's needed. Then once it reaches the high power transmitters, it's emitted over the air for carriage to the relay receivers and the gap fillers. The next couple of things I think I've already mentioned. Yeah, so the one important difference here is that when it comes to the STLTP data, it will be transmitted on that transmitter A. It will be seen by consumer receivers, but because it's not in the list of services that the consumer receivers are looking to receive, it'll just be ignored by them and will not impact the consumer receivers that see it. And in fact, they will retain their capacity for 4 simultaneous PLPs for service, for each service that's delivered, intended for consumer receivers. One thing the broadcast gateway needs to do is a little management of the timing with respect to those 2 releases of the STLTP. Note here that in this area that is occupied by the data going to the gap filler transmitters is a -T. Everything else says T in it. They're all released at the same time. The -T takes account of the fact that we need to go a little earlier with the data going to the gap fillers because it's got to go through more processes, and so we need to allow for propagation and processing delay in getting through the transmitter A, the high power transmitter, and then receive at relay receivers and feed it into the exciters at those locations. And so the broadcast gateway will offset the time based on what that number T turns out to be. So here we have a look at just the transmitter A to gap filler configuration. The signal is being received by the relay receiver, fed to the exciter, which is then transmitting, intending to be receivable out in the network. But the signal also gets back into the relay receiver antenna, and that's what we have to deal with. And so we have signal isolation, which can take the form of using antenna patterns and properly positioning antennas, the same thing you would do today with an on-channel repeater. But also because we've got the TSID in the signal, we can have the relay receiver be much more sophisticated in its separation of the two by using the channel impulse response information. So the challenge then is to handle that loopback signal coming back from the transmitting antenna into the receiving antenna. And if we do it in the configuration that we're talking about here, it would mean that the LDM signal would have a lower injection level because you've got some RF from the local transmitter that's not modulated at the enhanced layer level being added together with the signal coming from the transmitter A. And so that puts more emphasis on the need for the signal isolation and these advanced algorithms for separation of the two signals that I was mentioning. So if we look at the challenges in total, we have a dependence in recovery performance and the relative power of that loopback signal from the local transmitter, the isolation we can achieve, cancellation capability of the relay receiver, and also the both injection level and the received signal level coming from that transmitter A, the high power transmitter that's feeding the gap filler. Note that if we're using really low power gap fillers, we don't have worry about signal isolation and channel estimation and the advanced cancellation methods. But where exactly that low power, the low emitted signal power threshold is, I don't think we're ready to say yet. If we look at signal isolation, there are no relationships. Here's an example where we've got the injection level of the enhanced layer at 10 dB down, and it's a signal to noise ratio threshold based on the constellation encoding of 20 dB. We've got a good high performance receiver that can work at 35 dB, and the two receivers are modeled here with cancellation performance of 25 dB and 40 dB, and you can see the separation between the two lines over here. With the 25 dB receiver, we need 101 dB of cancellation. With the 40 dB receiver, we only need 93 dB of isolation. And then depending on the levels, those relationships change. Potential future extensions. We do R&D on in-band backhaul for figuring out just how to optimize delay and timing. We need to work on those requirements for improved or optimized reception that I mentioned. There's a possibility of being able to use a multi-hop system to provide backhaul, and a study needs to be done on that. And finally, we could use a 3-layer LDM. You see in the original LDM diagram, there was another layer down there, the feature extension layer, and that could be used and be completely independent for carriage of the backhaul data. If we still have to do work on that, but that's a real possibility. And if we move to case 2, here's one where both the core layer and the fixed layer are intended to be transmitted by all transmitters. So in this case, the Gapfillers would also transmit the data for the fixed layers. And now you have the possibility of using the Gapfillers for delivery of, for instance, 4K video, if that's what you want to do, or many more HDs, or however you want to use that lower power enhanced layer. You could now use it through the Gapfillers, where before we were saying, no, we wouldn't do that in case 1. And this implies that we would have to use a high-order modulation and coding combination, or mod-cod, in a separate PLP that we were using for the backhaul. And it implies 4K or 1K at least non-uniform QAM. NUQAM is a term that you'll hear repeatedly as we get more and more into ATSC 3. The one time I've used it here, but non-uniform quadrature amplitude modulation, which is what ATSC 3 uses. And then, of course, the high gain antennas that we were talking about. Oops. So to wrap up, LDM looks to be a useful way to implement wireless delivery without needing separate microwave or fiber delivery channels to a whole bunch of gap fillers. It's got advantages of lower cost, wider availability. You don't have to put anything special in, you just use the broadcast signals. We don't have a requirement for additional spectrum as we would with microwave, and it's fully compliant with the ATSC 3 standards. We do need a time control mechanism. That has to be added to the broadcast gateway. The fundamental STL stream will be the same. So it's a matter of releasing that STL stream twice at 2 different times and giving it, wrapping it in a way that it's identifiable. And then finally, as you saw in case 2, there's actually a case 3 that I didn't take the time to go into, that this concept can be extendable to even more functionality than we're proposing initially. And that will require the advanced signal isolation and core layer cancellation in order to achieve.